Okay. See, my name is Sathasivam, and I am a PhD student. Basically, I'm doing PhD in mathematics. Okay. So we'll start now. I will probably start sharing the screen. So we will start the broadcast. Okay. So these are the topics that we covered in the last lecture. So basically, we have did some introduction to numbers. So basically, we have studied the number systems, and then we introduced a concept called countability, and we'll say when we say a set is countable or when we say the set is uncountable. And we have also give some examples of rational numbers, and we introduce the function and we talked about the limits, right? So we'll do some problem related to each of this. So let's start with a few questions from the numbers. So before I start the problems, let me ask you, do you guys have any doubts in whatever we have done so far? In the first week, do you have any doubts? So anyway, you can think about it. If you have any doubts, by the end of the lecture, you can ask me, okay? So we will start with the problems. So here's the first problem. So if you have a number n, so here the n is an odd integer. So the question is, okay, which of the following below, which of these options are even? Okay. So it's n square plus 1, n square minus 1, n minus 1, and n into n minus 1 by 2. So the question is, which of these following is always even? I'm not telling n can be anything, but just you have to make sure it's an odd number. But this number has to be always even for whatever the odd integer you put. Maybe you think for a minute, and we will try to solve the problem. Or maybe I will just ask you, because so what type of lecture do you like? Should I give you some time to solve, or should I just start solving? So both works for me. Whichever the one you like, we can do that way. Okay, since there is no response, I assume that you're fine with both. So probably I'll start solving here. So see here, you look, your n is a odd number, right? So if your number is odd number, then you can see that n is of the form 2m plus 1 for some natural some m. Okay. So here the z means a set of all integers. So this is a set of integers. Okay. So what you know is if you have an odd number, then your n looks like this. Okay. So now what you have to compute is, let's compute n square plus 1, n square minus 1, n minus 1, and all these things, and see what you will get. Okay. So let's start with the first one, which is n square minus 1. Sorry, n square plus 1. So you have to compute n square plus 1. But since your n is an odd integer, so n is of the form 2m plus 1 for some m. So we substitute here, it is 2m plus 1 square plus 1. Okay. So I have to apply that formula, and you will get it is 4m square plus 2m plus 1, right? Plus 1. So what you can see here is this number can be written as 2 times 2m square plus m plus 1. Okay. So if you look this number is odd number, right? Because this is 2 times some number and you are putting plus 1. So this number is an odd number, and you are adding 1 to an odd number. So the whole number is an even number. Okay, so this is an even number. and this is even for whatever the n you put, as long as it's odd. So in fact, if you look here, so what we are basically using is the fact that if you have two odd numbers, a product of two odd numbers is odd number. Okay. And you can also see the product of odd numbers and the even number. This is a even number, so you can try to prove it. A product of a even number and a even number. And this is also even number. And here also you can write even number and odd number. Just if you write it as even number and odd number, that is also will be even number. Okay. So this is for odd. If n is odd, then you will have something. If n is even, then you have n equal to 2m for some n. Okay. And there is this. Okay, so if you use this fact and if you just multiply, you can prove all of these things. And in particular, we are just using these things to prove it. Okay, so basically you have odd number, multiply odd number to odd number to get a square, it will be odd number, and you are adding 1 to it, which is a even number. Okay, so let's come here and let's try to prove it. So you have n square here, and you have n is an odd number, so n square is an odd number, and you are subtracting 1 to it. So this is an even number, right? So this is true, this is true. So these two are always even number. So what about this one? You have an odd number and then you are subtracting 1 to it. What it will be? It will be even number, right? So this is also true. Okay, why? Because if you have odd number, that means n is of the form 2m plus 1. And if you are subtracting, so if you look at n minus 1, that is 2m. 2m is a even number. Okay. So now let's look at the last one, which says that it is n into n plus 1, n plus 2 by 2. Okay. Into n plus 1, n plus 2 by 2. Okay, so let's look at this one. So your n is of course, it is a odd number. Here n plus 1 is a even number and n plus 2 is odd number. So these two will be odd number, but this one will be a even number, but you are dividing by the 2, right? So it depends on the n. It can be either a even number or odd number. So for example, if you take, let's say, n equal to let's get a good n here. Okay, let's take n equal to 5. Okay, and if you substitute here, this is 5, 6, and you have 7 by 2. So if you cancel out, you get 5 into 3 into 7. So this is a product of 3 odd numbers, which is odd number. Okay. So in general, this need not to be true. There are examples where it can be true. For example, you take n equal to 3. So if you take n equal to 3, you will get the 3, 4, and 5. If you divide it by 2, you will get 3 times 2 times 5. So or you can get something like that. So this is a even number. So in general, you cannot say anything about this one. It depends on whatever the n you choose. Okay, so this is not always even. So this is wrong, and the rest of the things are right. Okay. So there is a similar assignment, similar question in the assignment. So you can try to figure it out how this is related to that. So okay, let's move on to the second question here. So this one is a little bit interesting. So what you have to do is you have to find. So recall. So if you have a rational number of the form p by q, now if you write a decimal notation for this, okay, if you write this P by Q is some, let's say, A dot, let's say, B1, B2, B3, B4, etc. If you write like that, if you write a decimal form of this rational number, so what you know is after certain stage, some of the terms is keep repeating, right? So if you have a rational number, what you know is after some stage, it looks like something like that. A dot some B1 to some Bn will be there. After what happens is C1 to some CR, it keeps coming. So I put the bar here to denote that CR will come, then C1, C2, something like that. So it will be repeating after some stage, it will start to repeat. Okay. So this one you might have known by now that you can write a decimal expansion, and if you have a rational number, the decimal expansion kind of start to repeat. But now the question is, suppose if I give you a rational number like that in a decimal notation, so how do you find this in a fractional notation? Okay, so basically I am asking you to find the fraction such that this holds. Okay, so let's try to solve this. So any idea how to do it? I think a similar kind of problem might be in the assignment also. So all you have to do is cleverly just manipulate this and you will get it. So you start with this. So let's call this as x, which is 0.6555. So it's the 5 is kind of repeating here. Now let's take what is 100x. Okay. So if you look at the 100x, this is 65 point. Yeah, so let's take the 100x. So it will be 5, 5, 5. It repeats like that, right? Okay, now let's take the 10x. It will be 6.55. So if you see what is the relation between these two, if you see it, what happens is after a term, this will be all the same, right? The decimal places are all the same. So if I subtract 10x from 100x, I will leave the decimal places kind of goes away. Okay, so that was the idea that we are going to follow. If you look at 100x minus 10x, this will be 65 minus 6, sorry, 65.555 minus 6 point. Okay, so if you subtract, what happens? This decimal places will cancel each other, and then it's basically you're subtracting 65 from 6 from 65, which is 59. So in this side, what you get is 90x is 59, and so you just have to compute x, which is basically 59 by 90. Okay. So that's how if you have a fractional notation. If you have a decimal notation and you want to go to the fractional notation, so you have to use a trick like that. Depending on where this C begins, you have to use the proper, you have to multiply with a proper number. Here I am multiplying with 100. In general, it's 100 will not always work. So you have to multiply maybe 1,000 or something. You have to choose these two numbers properly so that the repeating part that comes will you can just cancel out. So whatever remains is only how to deal with this. So, but pretty much the idea is pretty much this, but you have to come up with the correct number for each of the terms, each of the problem that you are working, it differs. So, so let's move to the some other, this is also an interesting problem. So let's look at this following. So which of the following number is a rational number? So you have a square root of 196, square root of 197, and square root of 225, square root of 200. So which of the following is a rational number is the question. So at least a few things you can directly say. if you look at 14 square, I mean, you have to just check all the squares, then you can look at the 14 square. So this will be 196. Okay, just to square it and you can see it is 196. Okay, so if you look at the square root of 196, and that is nothing but 14. Okay, and you look at 15 square, this will be 225. Okay, so if you look at square root of 225, this is 15. Okay, so these two numbers are clearly there. Now, what about these two numbers? So for this, you have to use a theorem that which was done in the lecture. So I'll probably take the hint. So the hint is if you take a nth root of a number a, which is basically it's an integer, both are integer. If you take a nth root of number a, it will be either an integer or it's an irrational number. Okay, so this was in the notes, in the lecture notes. You can just go and look at it. So now what we know is it's either an integer or irrational number. So, but here you observe 197, let's say, is between 196 and 225, right? So let's write here. So 196 square root. This is less than square root of 197. Strictly less than. Sorry, strictly greater than. And 197 is strictly less than 225, right? So we have this. But this is 14. And this is 15. Okay, so if you look at the square root of 197, it lies strictly between 14 and 15, but the square root of 197 is either an integer or irrational number. Okay, if it's is there any integer lies between 14 and 15? After 14, the next integer is 15, right? So this number is neither a 14 or a 15. So, but it lies inside. It lies between 14 and 15. So it has to be an irrational number. Because if it is an integer, there is no other integer between 14 and 15. Okay, so it cannot be integer. So what is the other possibility? The other possibility is that it is an irrational number. Okay, so this one. So this one is a irrational number. Okay, what about this one? So you can make the same kind of argument. So this number, whatever the square root is, that is again, I'll change the same thing. Here you have 196, square root of 200, let's say I put, and it's a square root of 225. So you look at this number. So this number is again lies between this and this. But this will be 14 and this will be 15. But check what about this one. So it cannot be an integer, because if it is an integer, either it's a 14 or 15. Between 14 and 15, there is no other integer. I mean, same argument, whatever we do, you can prove that square root of 200 is also a irrational number. Okay, so this is also a irrational number. Okay, so you have I think you might have an assignment problem of a similar type. So the hint is to use this. Maybe not exactly goes like this, but the idea is to somehow use that and try to get it. Okay, so before so these are the problems I have for numbers, and then we'll move on to countability. But before going into that, I'll just make a remark. It may not be very useful for a calculus course, but it's an interesting question nonetheless. So when we introduce the real number, we see the real number like geometrically like a number line, right? Okay, so this is a 0, and then you can geometrically write it. So let's say I fix this as a unit length 1, and if I want to say where is 1.5, I can construct it, right? because this length is 1, you take half of this, okay, and then you move this length here. So this number is, let's say it's 1.5. Okay, I can construct like that. But if I ask you what is the square root of 2, okay, so how do you, in the number line, how do you say where is the square root of 2? So it's not very easy, right? Because if you have a rational number, you can at least point out, okay, you have to go further divide multiple times and then you will get it. But this number you cannot directly say. So the question is, how do you know such a number is even a real number? How do you know a square root of 2 is even in the real line? Okay. So even though one can geometrically say this real line is this line is the real line, etc. Uh, what actually happens is, see, we have integers here, and then we construct the rational number, which is basically set of all p by q. Okay. So this we constructed, and then we have to go to real, right? So I think some of you might have seen the complex number. If you look at the complex number is easy to see. This is a plus ib, such that a and b are in real numbers, right? So integers one can easily describe it, rational one can describe it, and complex also one can describe it. Okay, but if you notice, whenever we do the real, we kind of always tell it's a number line, it's a geometry or something. We never try to describe it, right? So the reason is, it's not that it's a geometry or something. There is a description of R, but it's much complicated to actually construct it. From going from here to here, it's easy, and going from here to C is also easy. But going from Q to R, it's not very easy. So there is a construction of real number. There's something called, let's say, DD kind cut. So this is a construction. So there are two type of construction. One is using the DD kind cut, and there's another construction which uses Cauchy sequence. So you may not heard of these names, but there is two construction of real number, and one can prove both construction are actually the same. So yeah, there is no two real numbers; it's the same real number. But these objects are very complicated to construct, and hence most of the time we will not do it. Okay, and it's not very interesting for whatever the purpose that we are going to do. So you can just assume it as some number line, and you can see all these numbers are here. But if you just want to look at the square root of 2, it is interesting because there's some geometry behind it. So if you want to look at let's say square root of 2, okay, and you want to see, okay, if I start from 0 here, where will I map square root of 2? You can map it. So the way you do is you take the right angle triangle. Okay. So you take a right angle triangle in which both of this side is 1. Okay. Then what is this side? So this side is basically a number x, let's say, but the property of is x square is equal to 1 square plus 1 square. This is a Pythagoras theorem I'm using. So this will be 2. So you will get x square equal to 2, right? So basically, this x is nothing but the square root of 2. Since you can construct a right angle triangle like that. I mean, it's easy to construct a right angle triangle. Put a 2 number, put a right angle, and just draw a line. And whatever this length of this hypotenuse is the square root of 2. So this number is basically a rigid number, and this number is kind of well known from the Greek time itself, okay, because it's a theorem or there from the Greek time, and they used to believe that this is actually a rational number, okay. So it's not a rational number, but Greeks used to believe that this is a rational number. So you might have seen this proof, right? If p by q is root 2, then you take a square and then you do some proof by contradiction, right? So this is a very popular proof by one of the Greek mathematicians, but people are not ready to accept it because they want to see the universe is like a perfect, and to say something is irrational makes it not perfect. So some guy told him, and they just yeah, so they don't want to accept at that time. But So that's why there is a historical significance behind this proof also. So anyway, that's just a story I want to tell. Let's move on to the second part. So here it's about the countability. For I will probably just recall the countability and then we'll go. I will not do much. I will just recall. So if you have a set A, you say the set A is countable if there is a bijection F from a natural number to A. Okay, either natural number to A or from a set uh, let's say 1 to n to A. Okay, so in this case it is countably finite. If you have a bijection from natural number to A, then it is countably infinite. Okay, and this is finite. Okay, and we say a set is uncountable if it is not countable. Okay, so uncountable basically equal to not countable. I mean, I'm not saying anything in, yeah, but anyway. So I think you got the idea. So now what happens is I have a two set A and B such that the set A is countable and the set B is uncountable. I haven't write the question here. The question is then whether the set A union B is countable or not. Okay. A union B is countable. So you have two set. You have two set and both of that are countable. Sorry, one is countable and another one is not countable. So the question is the union countable? So can you tell me what is the idea? See, we can make it a little bit discussion also. If you have some questions or some comments, you can always ask. Or if you have some answers also, you can always tell. So it will be like more of a discussion than I'm just telling you. That would be makes things better. So maybe you take a few seconds, or maybe 30 seconds or something, so that you can think about it. So what are the countable set that you know of, and what are the uncountable set you know?
Sir, set of natural numbers are countable,
Okay. So
and
let's.
rational set of rationals.
Okay, these are all countables, right?
Yes, sir.
Okay, I can take this. Okay, can you tell an example of a set which is uncountable?
Sir, set of irrational numbers.
Okay, set of irrational numbers. Okay, and what else? Can you tell something else?
Open intervals, sir. Any open interval. Sir,
Open
any
interval.
intervals.
Yeah,
Closed
any
or
interval. Yeah, closed or open. Yeah, that's nice.
set of reals.
Mm-hmm.
Set of reals.
Set of reals. Okay, yeah, this is the interesting one. Okay. Okay. Now let's try to take a union and see. Since we have so many sets now, we'll just take a union and see. Okay. So you know how Q complement is countable, right? This may be interesting because if you have, okay, I'll tell you why this problem is even interesting. So if you have two countable set A and B, so maybe I'll write here. I think this might be done in the class, but I'll write here anyway. If you have a two countable set, so if you have a set A, B, if both are, let's say, countable, then what you know is A union B is also countable. Okay. So this we might have done in the class. In fact, what you can say is if you have a countable collection, okay, let's say you have A1, A2, etc. Let's say AN, etc. So you have a countable collection, or in general, I can tell something like that. Usually people use the different notations. I will probably use it. So you have a collection of set AI, okay, where I is in some index set I. Okay. So maybe anyway I may not don't want to use it because anyway some of you might be first years or something. So let's not do too much. So let's say you have a collection of set like this. Okay. So you have infinitely many collect set, but what we know is if you take all this set, this is countably many sets are there. So basically, it's either a finite number of set are there or infinitely many set, but then it is indexed by natural number. So basically, you have a countably infinite many sets. Then if you take a union of these sets equal to 1 to infinity AI, so you can prove that this is also countable. If all of these AIs are countable, if all of these are countable, so all of these are countable, then you can prove that union is also countable. So if you want to look at the proof is similar to whatever you did with the Q is countable. Okay. So it's the same thing. Basically, you count like this. Okay. So that's not much. So in some sense, if you have two sets, then the union is countable. This is like well known. So the question is, if I change one to be uncountable, can I still get a countable? Because see, I know one of them is countable. So if you look here, let's say we can take this n as this n you can take, and you can take a q complement. If you take n union q complement, well, you will get some set, but one has to see how this set looks like. Okay. But one of the easy thing what you take is you take n and probably you take the r. Okay, so this is an easy example. Since you just need one example to prove if it is a false. So let's say you take n and r. So I will erase here. So let's take a equal to n, b equal to r. Now you take the union a union b. This is nothing but n union r. And what is n union r? Because all the natural numbers are real anyway. So n union r is nothing but r, nothing but just a real number. Because all the natural numbers are also real numbers. So a union b is nothing but just r, and we know that r is uncountable. Okay. So the answer for this is false. Okay. So true is not true, false is true. But so this question actually ask you another question. Okay, I know the union. Now what about the intersection? So that was a natural question, right? So let's do the intersection also. So what about A intersection B? Is it countable? So you have a true or false here. Okay. So what we know is A is countable and B is uncountable. Okay. So in this case, if you take A intersection B, so A intersection B is a subset of both A and B, right? So since it's, I think somebody has some questions, so probably I'll go here and see. Oh, okay. I think you guys are typing here. Can you see the recordings of this live? Yeah, you can see the recording of the, yeah, you will see it. We'll post it in the YouTube and we will send the link to you. Yeah, so on the, yeah, and it is countable, yes. So probably I will try to bring the chat somewhere here. Maybe just give me 1 minute. I'm sorry about that. I didn't notice this earlier. So, I'm just trying to bring the chat up here so that we can see. Okay, probably I might need uh, okay, maybe from next class I will try to bring the chat there. Maybe I have to join with a different account, I think. It's not very direct. Anyway, so I will do this next class. Maybe let's not waste time here. But yeah, sorry about that. We can see if you can see chat here. Yeah, I can add a chat here. Okay, we will continue. Anyway, now I can able to see the chat, so let's continue. Yeah, so as you have seen, as you have said that this is a countable. Because if you look A intersection B, A intersection B is both a subset of A and a subset of B. But what we know is A is countable, right? Since A is countable and A intersection B is a subset of A, so you use this theorem. A subset of a countable set is countable. Is countable. Okay, so this is a let's say it's a theorem. So the proof is not very hard. So see, you can try to prove it by yourself if you haven't seen it. Okay, so the proof is not very hard. So I will just leave it as an exercise. You can see it in like in every book it is available, so you can look at it. Okay, so since A intersection B is a subset of A, it is also countable. Okay. So intersection is always countable, but union is not countable. Uh, in general, union is never countable actually. Okay. Okay. Let's prove that also generally. So if we have A union B, and let's say B is uncountable, so then what happens is A union B is uncountable. So since we have other examples, right? For example, n union q complement, one can see, so one can always ask whether this is countable. Because what I take is this example, it makes my life easier, but one can always argue, okay, what about this? So let's prove it directly. If you take A union B, it is uncountable. So why? Because this B is contained in A union B, right? So if A union B is countable, then what happens? Yeah, intersection is always countable. Yeah, because you remember this theorem. Okay, a subset of a countable set is always countable. Okay, since this A is countable, I mean it's not, intersection is not always countable. Intersection is countable if at least one of the terms is countable. So you have A intersection B. So if either A or B, at least if one of them is countable, then A intersection B is countable. Otherwise, it's not. Okay, so this I will probably erase here. Okay. Otherwise, you will not get it under some condition. And similarly here, if one of that is uncountable, I don't care about what is A. So R intersection irrational. So R intersection irrational is basically irrational, right? And irrationals are uncountable. So if you take intersection of two uncountable set, that's not very clear whether it's uncountable or not. That you cannot directly say. Okay, maybe I can give some example also. Anyway, since we are doing it, let's solve that problem also. But let's proceed with this here. So what we have seen here, so okay, maybe we'll go systematically. Okay, let me erase it and we'll go systematically. So you have the theorem. So remember this theorem, a subset of a countable set is countable. Or it's in fact it's any subset of a countable set is countable. Okay, so this is the theorem. Let's start with the question. So if you take A union B, sorry, or A intersection B, let's start with this. Okay, if let's say either A or B, okay, let's in some sense it doesn't matter. So I will take if A is countable, then what we have is A intersection B is a subset of A, and hence A intersection B is also countable, right? Okay, so if one of the thing is countable, then we got intersection is countable. Okay, so what is the other case? The other case is both A, B, both are uncountable. Okay. So then what you can say about A intersection B? So in this case, what happens is things become complicated, and in general, this need not to be countable. It can be anything. It can be finite. It can be countably, infinite. It can be uncountable. Okay. So in general, you cannot say anything. Why? Because I can tell you one example here at least. So let's take A as 0, 1. Okay. And let's say B as 2, 3. So if you look, okay, now what is the, because both are uncountable, we know. Look at the intersection, and that is 0. Sorry, it's an empty set, right? So it is a, what, it is a, yeah, so the empty set is also countable because there's nothing to count here. So usually you take a non-empty set as countable. So this is countable. Okay, because it's empty set. So empty set is, I mean, there's nothing to count anyway. So, but on the other hand, if you take, let's say, you just take a different example. Let's say take both A and B as, let's say 0, 1. Okay. Then if you look at A intersection B, this became 0, 1 again, and this is uncountable. I mean, you can produce much complicated example than this to show that A intersection B is uncountable, but I mean, one can produce a number of examples, but the idea is A intersection B in general, you cannot say if both of them are uncountable. But if both of them are, at least one of them is countable, then A intersection B is countable. Okay, now let's look at union now. So what we have seen is A union B, if both A and B are countable, then the union is countable. So this is again, this is not, this is easy only, but it's a theorem, let's say. Okay. So this I am not going to prove it. It's done in the class. It's the same thing like you prove that Q is countable. You just have to write the same way. And you can prove in much general. So since I already told you, right, you can take a countable union. You don't have to take a union of two sets. You can take how many ever sets you want. This is the case if both of them are uncountable. So the other case is if one of them is countable. So you take A union B. And but what here we have is B is uncountable. Okay. So A can be either countable or uncountable, doesn't matter. As long as B is uncountable, what we will get is A union B is uncountable. Okay. So let's prove this one. This will be easy to prove. So we'll go by contradiction. So suppose if you assume that A union B is countable, we want to prove it is uncountable. So instead what we are telling is, okay, let's assume it's countable and see what happens. So if it is countable, then what happens? B is a subset of A union B, but then A union B is countable, right? What does it tells you? See, use this theorem. There's the theorem, yeah. So this is the one of the important theorem. So any subset of a countable set is countable. So that means B is a subset of A union B, and A union B is countable. So B is countable. Okay, but you start with B is uncountable set. So that now what you got is B is countable. That is not possible. Okay, so there is a contradiction. So the contradiction arises because you have the assumption that A union B is countable. So this statement cannot be true, because if it is true, then you will get something which should not happen. So this is not a possibility. So what you get is A union B is countable. Sorry, A union B is uncountable. Okay. So this is the kind of the relation between union and intersection, and there is a product also. So, but we will just skip those things. Okay, so let's move on to this one. So here we will come to the functions. So when I write, so I have two functions here. One is the square root of x, another is 4 minus x square. Okay. So the question is, what is the domain of f compose g of x? So if maybe if you compute f compose g, this is nothing but f compose g of x is nothing but square root of 4 minus x square. So this is the question, but probably I will prove it. I mean, I will show the solution, but since it's like the first time, I am not going to do too much computation. I will show it geometrically. Okay. So we all know how the x square curves looks like, right? So I mean, let's do geometry. I mean, one can prove it algebraically without doing any graph, etc. But let me do geometrically for this time. But yeah, the proof by geometry is not a proof per se, but we'll just give the intuition. So x square kind of looks like that. It's kind of like a parabola. So y equal to x square is a parabola. If you have studied in your probably 10th grade or 12th grade, it will be there, right? Now what I'm doing is I'm taking minus x square. So let's go one by one. From inside we will go. You take minus x square, right? So minus x square means basically you are flipping this, right? So whatever the value of y now became minus y. So minus y means it has to be it just flips the other way around. So this is minus x square. So I'll write here. Okay. This is, let's say, x-axis and this is y-axis. Okay, and this curve is minus x square. Okay, now what I'm going to do, I'm adding 4 to it, right? So adding 4 is same as like okay, let's say y equal to 1. Okay, so let me ask a question here. Maybe something. So it's a general. Suppose I have a function like this. Okay, so y equal to f of x. So what is f of x plus 1? If I add f of x plus 1, that means every point I'm adding 1 above, right? So y equal to f of x plus 1 is something that goes just above. Exactly like this, but just go 1 above. Okay. So you just translate this by above. You just move it up. That's all. Okay. So in this case, I'm adding 4 to it. Sorry. In this case, I'm adding 4 to it. So I'm going to move it 4 steps up. We'll write here. So this will be something like this. Okay, so this point is 4 now. So x is, and these points you try to compute what are these points. This point is basically -2 and this point is 2. Okay, so this is the number. This is what you are having for minus x squared. Okay, you can compute this. So basically, you just put -2 here inside this. So it is -2 square, which is basically 4. It's 4 minus 4. This is 0. So this point and this point is basically 2. Okay. So now what happens is, if you look here, the image of G is positive if you are in this domain. Okay. So in the domain of when x is between 2 and -2, g of x is positive. Okay. And whenever it is in the other direction, which is basically minus infinity to -2 union 2 to infinity, so g of x is strictly less than 0. Okay. Now let's look at what is my f. My f is basically a square root function, right? And the square root function domain is defined only when you have a positive number. Whenever the x is positive, only when the x is positive, the square root is defined, right? So to apply f to compose with the g, you have to make sure that g has to have a positive range. So g has a positive range only when x is between -2 to 2. Okay. Otherwise, the square root is not defined. So whenever g is negative, the square root is not defined. So g is positive only when -2 less than x less than or equal to 2, and only in this range you can talk about f composition G. Okay. So if you look at f composition G, it is defined only on this range, and so its domain, if you look at the domain of this, so the domain is -2 less than or equal to x less than or equal to 2. Okay. So is that clear? So if it's not clear, you just stop me and ask. So you can unmute your mic also. So, so one can also look at the range of this function. Okay. So can anyone want to guess what's the range of this? I mean, the question is only this much, but since we started, let's try to analyze the problem completely rather than just leaving it here. So, what is the range of this? Okay, here I have. Probably I'll just do it like this for now so that you can see it completely. Yeah, so he's correct. Can we use Venn diagram to find it? So you want to use Venn diagram to find which one? So probably you type there and I will just look into that. So there's a message that says, can we use Venn diagram to find it? So to find the range. So how do you use Venn diagram? So I'm not sure how to use Venn diagram. So, okay. I was just asking. Okay. So yeah, at least I don't know how to find how to use the Venn diagram. Maybe it will be there, but I'm not sure. Sorry about that. Okay. So let's try to find the range of f compose G. So somebody said it's 0 to. So let's check if it is correct. Okay. So what is the range of G? If you look at the range of G, well, it can be from 4 to minus infinity. That's the range of G. But we don't want it on every domain. We only want G on this domain where it is positive, right? So the G is only on this domain, right? So in this domain, if you look, the range of D is 4 to 0, okay? So you look at the range of G. So range of G is nothing but 0 to 4. Okay. So now what happens is your F compose G. So if your F here, now your F is composing on G only on this range, right? So now we have to just look at basically it's same as telling F of uh, X. Sorry, it's basically the range of F of X. But you are just restricting the function to just 0 to 4. So you are restricting your domain to only 0 and 4. So let's look here. It's a square root of x function. Let's say I think it goes something like this. And you are only looking at the range from 0 to 4. And if you look here, and this range is 2. So the range is 0 to 2. Okay. Okay, so the range of the function you can see from here, it is 0 to 2. Because what happens here is, I mean, G is some random function, I mean, G is some function, but the range of the G is basically 0 and 4, on which the F acts, right? So that's what we are having. Okay, so the range is 0 to 2, and the domain is the other one. Yeah.
To find the range of the function G composite F, is there any analytical method we can follow step by step? Like
Analytical method means oh.
you have told a graphical method.
Oh, okay, okay. See, when I said graphical method, what I'm meaning is, see, I'm just using this graph to tell you that g of x is greater than or equal to 0 in this region, okay? But one can say without the graph, because if I give a complicated g, then you drawing the graph is not easy, right? So one can directly do it. Probably I will do that also, since you have asked, then I will do that also. So let's look at the, so basically what you are looking at is when the G is positive, I have to find the numbers here such that G is positive. That's what I want to do. So what I did is I just draw a graph from which you can directly see, okay, from this region to this region, G is positive. So you can look, G is positive in this region, and everywhere else it's negative. So I just use the graph to tell this. But if you want to do it without reference to the graph, of course one can do. And that was the interesting part, because you cannot always draw a graph. And ideally mathematicians, see, this is a calculus course, right? So it's fine to do this. But if you go higher mathematics, people will not, so you cannot draw something like that and call it a mathematics. So let's do the other way also. So what I want to find is, I want to find x. So I want to find values of x. Values of x. Such that my g of x is positive or non-negative. So why I want to find this? Because my f can only, see, f is a square root function, it can only act, its domain is restricted to positive region, right? So I want g of x to wherever it is positive, wherever this range is positive, then at those points I can define f. Otherwise I cannot compose with g on the places where it is negative. So what I want to find is the value of x as such that g of x is positive, right? So let's look at what is g of x. G of x is nothing but 4 minus x square. So 4 minus x square is greater than or equal to 0. So this tells you 4 is greater than or equal to x square, or the other way around you can write it's x square is less than or equal to 4. Okay, so if x square is less than or equal to 4, then what about x? So here this directly tells you uh, minus 2 less than or equal to x less than or equal to 2. Okay. Why? Because see, it's a square function, right? So square function is kind of symmetric. So when you take the square root here, you will get both the square root, both the negative square root as well as the positive square root. So this region you will get directly. So instead of 4 minus x square, even if you get a complicated function, whatever it is, you can just, solve something like this, and then you will end up with the equation like that. And then you have to solve for whatever the x is. If there is a square, it will be easy. Sometimes there can be a sign here, but then you have to use the property of sign. Here we are using the property of x square. Otherwise, you have to use the property of sign. And some such things you have to do to get this. Okay. So, if you want, I can do it a little bit more. So, you take the positive square root on both sides. So, you take a square root of x is less than 2. Okay. So, when I write the square root of x, it's a positive. It only gives you a positive square root. Okay. So, I will not get a negative square root, but this function is basically symmetrical. So, from here and here, it is symmetrical. So, in this region also, I will get the same kind of value. Okay. So, the square root of 2 I will get. Yes, but square root of x is nothing but x here. So square root of x square, which is x. So in this region also I will get, but this is a positive square root. So basically this I am taking only the positive region. But then since this function can, whatever comes in the negative region also, it maps symmetrically. So I will get this region also, because this region also maps to, has the same property here. Okay, basically you take the square root here and check that that is true. Okay, but whenever you do analytically, you have to come up with, you will get a function here, and then you have to use the property of this function to solve it. And whatever the function may be, depends on that, the things will change here. Okay, so let's go into another problem here. So it's a similar kind of problem again. So, but instead of comparison, you only have one function here. So you have a function g here, which is a modulus of x, square root of modulus of x. So you want to find the domain and the range. So it's a third option. Okay, domain is whole of R. Okay. So, and what about the range? Range is 1. Okay, I think you might mean option 1. Okay, somebody said option 2. So let's say Sandeep said option 1, and yeah, the other arbitrate. So he said option 2. So let's check. Yeah, so Sandeep also changed it. So there's only one option now. So yeah, so there's another answer. Okay, so many people are supporting option 2 here. So let's see it. I mean, it's not very hard to see it, but let's see it. See, the harder problems will come in the later part of the course. Okay, so now it was a little bit easy problems. So, but anyway, we'll try to do it. So you look at the mod x function. So if you look at the mod x function, this you draw like this. Okay. So whatever the, see, again, my square root function, if you look, it is only defined on a positive region, right? It will not be defined on the negative region. But my mod x function is a nice function. What it does is it takes even the negative values and then it makes it positive, right? So the image of the mod x is always positive. We cannot say positive, it's always non-negative, okay, because 0 can be there, so it's not always positive. So the square root can be then applied to it. See, even though it just looks like a one function, it is basically a composition of two functions. One is the mod x and another is the square root. Okay, so since it is the mod x always gives me a positive value, the square root can be applied to it on all the times. Okay, so the domain is basically minus infinity to infinity, because I can apply square root on any x. So whatever the x you take, let's say you take minus 2, and when you apply modulus, it became 2, right? And the square root of 2 is defined. Okay, as long as it's a positive number, square root is defined. So does not matter if it's a negative number or positive number. So domain is this. Okay, what about the range? The range is the range of the mod x. Okay, you take this, and then in the range you apply f to it, or apply the square root to it. So the range of the mod x is basically 0 to infinity, in which you apply the square root. Okay, so basically you see this, and then you kind of flip it to the x-axis here. So whatever the y-axis you come, so when you do the comparison, you take the y-axis, and then you can just flip it to x-axis, and then you apply whatever the function you want to do. So the range is 0 to infinity, and then here you are applying the square root of x. Okay, and that will gives you all the range here. The range will be 0 to infinity again. Okay, so this is the correct one. Okay. See, sometimes at least when you do calculus, the intuition actually really matters. So you try to see, one can do like this. Okay, I mean, one can compute like this. That is fine. Uh, that is what you do when you don't have intuition. Okay, so when you go for a multivariable calculus, or when you go for a vector calculus, then you cannot do all this kind of intuition. So these intuitions are all mostly gone. So there are manifold theories, there are other theories. See, there are group theory, and some groups are all manifolds, and there you can do calculus. Okay, so now you're doing calculus on the real number, then you do calculus on the group. But maybe not the calculus on the group, but you can do some kind of a smooth structure there. But the thing is, those kind of things are complicated, where you cannot have this kind of intuition. Okay, so whenever you have the intuition, you can try to use it. So it's sometimes good to see it through the maps, etc. So later part you have to do analytically, but nowadays this is a good time to develop some intuition. Okay, so let's start. So now we finished the domain. Now we move on to the limit section. So let's start with this problem. So you want to find the limit of as x goes to 1, 2x by mod x. And let's see what's the limit of this. Is any idea? Okay. So the limit is 2. Okay. Okay, so let's see. So the limit must be 2. Let's try to prove it. So you have 2x by x. Limit does not exist. Okay. So you can explain why limit does not exist if you have some idea. But let's see. Okay, so see, we are looking at 1, right? So we are looking at the 1. So whenever you do the limit, so here I have, so x is, here is 1. So what I'm going to see by the doing the limit is I'm going to approach 1, and I'm going to see what happens to my f, right? That's what basically I'm trying to do here. So whenever you are approaching here, see, you can take a small enough neighborhood and you can approach. You don't have to approach from here, because since you are approaching to 1, it doesn't matter. You can restrict your function to a smaller domain here. So you can. So what I'm trying to say is, since 0 is here, so you can take a small enough domain here, and then you can apply the limit only inside this. Okay. So when you do that, what you can see is, you can, without loss of generality, you can assume the x to be 1. Oh, sorry, x to be positive. Okay. You don't have to take the negative x. Take the x to be just a positive. Okay. So you can assume x is strictly greater than 0. This you can do because you are doing the limit. Okay. So in that case, what happens is mod x is nothing but just x. So you have 2x by x. Now we are taking limit as x goes to 1. Okay. So this is nothing but you just cancel out x by x. So cancel out this, and then you will just get 2. Okay. So this part is easy. So let's move on to the other part. So in this case, what happens is the x approaches to -1. Instead of 1, x approaches to -1. So you can give a try for some time, and then you can do. So in the assignment, what happens is you have the x approaches to 0, right? I think in the assignment there's one problem where the x will approaches to 0. In this case, you have to look at the right hand limit and left hand limit separately and see whether that is the same. Okay, so that I'm not going to do. That was assignment, so that is for you guys to try. But here we can try this one. So it cannot be 2, right? Because see, there is no 2 in the front. In that case, there is a 2 here. But now there's no 2 here. Okay. So in this case, what happens is, see, my x is approaching to -1. But see, again, I will just draw a graph here. So I will have -1 here. But I just want to know what happens when you are going closer and closer to -1, right? So in some sense, I don't care when x is here. I care when x is closer and closer to 1. Not exactly at 1, because at 1, what happens is, okay, at 1 also sometimes here it makes sense, but if you take 0 or something, it does not make sense at x equal to 0. But at 1, I don't care what happens. What I actually care is what happens as I move towards 1 -1, right? So I don't care what happens when the x is here. I care when the x is going closer and closer. So with the laws of generality, I know I can restrict my domain of investigation to a small enough neighborhood, whatever the neighborhood that I'm interested in. Okay. By doing that, I can assume without loss of generality. So I can assume that x is strictly less than 0, because I can just restrict to this neighborhood. My investigation of the limit does not changes, because I only care about what happens as the x approaches to -1, right? Okay, now x is less than 0. In this case, what happens is the mod x will be -x. Okay, so then we are looking at something like x by -x, and then you're looking at limit x tends to -1. Okay. Well, now it doesn't really matter whether it goes to -1 or -2, because you're going to cancel out the x, and this will be -1. Okay. So when it is a 0 by 0, okay, let's say something like let's say limit x tends to 0, x by mod x, something like that, let's say. Okay. In this case, what you do, see here I cancel out x and x. Can you cancel out x here? Let's say you are approaching from the right side. Okay. In the right side, what you have is just mod x is just x. As if you go in this direction, mod x is just x, right? So can you cancel out x and x here? So that was the question that you have to think about. You think, and then you will get the idea. So I may not be, I'm not going to prove it there, but I think you have to think, and then you will get the idea. Okay. So anyway, we will leave it for that as exercise. But I'll just tell here, because see, I'm approaching to 0, okay? But I'm never at 0. So whatever the x is not 0. Okay, so that you take in mind, because all I'm saying is I'm approaching to the 0 in this direction. So I never say that I don't care what happens at 0. 0, it can be anything. I only care what happens when I'm going closer and closer to 0. Okay, so whenever I'm closer at 0, I'm never at 0, right? So this x is not a 0. That's the idea. Okay, x is not 0. When x is not 0, you can do something. And then you try to find both limit and see what happens. Okay, but anyway, that was the exercise. We will not do much. But the idea is something along the lines you have to do it. Okay, so let's move on to this problem. I think this is quite easy, but let's see. So it's a true or false problem. There's not much there. Yeah, it's true. Okay, somebody, yeah. So I think most of the people are telling it's true. So any idea why? Yeah, yeah, exactly. So this is a true uh, in real number, right? Because real number has this property. Uh, yeah, so it's a field, but yeah, the thing is that not all of us know the field, right? So yeah, so real number of field and all the field has the property. Yeah, that's true. But for our whatever we want to do, the real number has this property, right? So once the real number has this property, uh, this is just a subset of real number, right? So basically x, y, z belongs to q complement is what we are writing, but q complement is a subset of real number. In particular, this x, y, z are all real numbers only. Even though I'm writing some different, I mean, saying it's it's a irrational number, but irrational numbers are real number. So the statement holds true for all real number, in particular for irrational number. So this is true. So there's not much to do here. It's just that this Q complement is basically a subset of R, and any statement that holds true for all real numbers has to hold true for a subset of that, right? So set of irrational field. No, set of irrational is not a field. Uh, in fact, even the additive group. I mean, if you add it to irrational number, it's not an irrational number, right? So it cannot be a field. So you take, let's say, pi or let's say square root of 2 plus square root of 2. If you take this will be 0, right? But 0 is not a rational number. Okay. Yeah. Okay. So anyway, if some of I mean, not everybody might have done the field. So for those who does not know the field, it doesn't matter. So you can just ignore it. Oh, so already got the answer. Yeah, nice. So this is another problem here. Yeah, so this is true. It is true. That is the claim. So let's see it. Here I have x square minus 1 by x minus 1. So you just apply, it's a square minus b square type. So you apply x square minus 1 square is basically x plus 1 into x minus 1 by x minus 1. Okay, now many of you said it's true, but see, if I put a 1 here, what you get is basically 0 by 0, right? Y I can cancel it out. So if I put a 1 here, then it will be 0 by 0. So, but you are cancelling out. So why? I mean, if you cancel it out, and if you substitute x equal to 1, you will get 2. That's clear. Yeah, exactly. Because you don't, yeah, because the x is never 1. X is approaching, exactly. So x is approaching 1, but it's never 1. So that was the important point that you have to do. And then you just, it's basically the limit of x plus 1 as x approaches to 1. This would be 2. So I think it has done in the lecture also, but I just want to tell this again. That because most of the time what happens is you will be at a 0 by 0 form, because whenever you find a derivative, so later you will study something called derivative, which is the important part of the calculus course. So when you study the derivative, what you do is you will get something like some people write del x by something, you will get here. So let's say del y by del x, something like that you will get, and then limit of del x approaches to 0. So what we know is when del x approaches to 0, we know that the del y also approaches to 0. So if you see, then it is basically 0 by 0 form. It makes no sense. But it is never 0. That's what's going to make a difference. So most of the time what happens is when you apply that, if you directly substitute it, you will get 0 by 0. But the interesting part about the limit, it kind of tells you, even though both things goes to 0, it will tells you in what proportion it goes to 0. So the limit in some sense is a little bit more interesting. Okay, but anyway, this is not important. So let's move on to this problem. So this you might have to work it out a little bit. So you have to solve the following inequality, where this is basically the norm. Norm is basically nothing but the absolute value. Okay, so absolute value of 3 minus 1 by x is less than or equal to 1 by 2. So what does it tell us about the x? So it's option 2. Okay. So maybe let's give a little bit time for other people also, and then we'll start to prove. Okay. So what is the pattern of the exam? Okay. I think we don't know. So see, you probably send a mail to NPTEL. They might have able to tell you what kind of a question will come there. So we are just taking the thing, and we are not involved in taking the exam question paper, etc. So we have no idea. Okay, if you guys done it, we can probably do some more questions also. There's not many questions there. So yeah, so most of the people got 2. So probably we'll try to do it here. Okay, so let's start here. So you want to do 3 minus 1 by x. This is strictly less than 1 by 2, right? So see, the modulus is less than something. That means what? That means minus 1 by 2 less than 3 minus 1 by x less than 1 by 2, right? So if you look at mod x minus a less than some, let's say epsilon, that means it means minus x less than x minus a less than epsilon. In fact, you don't even need this. You just need mod x is less than epsilon. So that means minus epsilon less than x less than epsilon. Okay. Yeah. So that is right. So you have this, and then basically the rest is just computing from here. So you just subtract 3 on the both sides. It's minus 1 by 2 minus 3 less than minus 1 by x less than 1 by 2 minus 3. So if you do it, it will be minus 7 by 2 and minus 1 by x less than minus 5 by 2. Okay. And then now you have to subtract, multiply with minus 1. Now you will get 5 by 2 less than 1 by x less than 7 by 2. Sorry. Yeah. And now you have to take 1 by x on both sides. Right. And just 1 minute. Yeah. If you take 1 by x on, just take the reciprocal of it. So you will get 2 by 5 less than, sorry. You will get 2 by 7 less than x less than 2 by 5. Okay, so this is what you get. So from here to here, so what is the step that we are using? So basically you have something like 1 by a less than 1 by b, right? So what you can say about a and b? And can, so basically since many of you gave the answer is basically b is less than a, if I'm right. Right? This is what you have done it. But is it always true? Yeah, exactly. It is true if and only if both of these are positive numbers. Okay, if 1 by a and 1 by b are positive numbers, then this statement is true. Otherwise, this statement is not true. So that's why you want to first multiply this with a -1 so that this numbers become positive. Then you can use this. Okay. So this statement is true provided uh, A and B are positive. Yeah, definitely it is positive because otherwise it doesn't make sense. 0, it doesn't make sense. So it's positive. It has to be positive. Okay. So let's do this one. Zero. Okay, nice. He is very quick though. Probably next time I come up with some hard question just for you so that you will take time. Okay. So we'll just show the hint and you can use it if you want. So you have to use this formula, trigonometric formula, you can use it. And then this limit, let's assume that you know, okay, it's not 0, it's 1. Okay. So let's assume that this limit also you know. Now you can try to compute. You think the limit is 1, okay. So let's see. Maybe one of your answer is right, but it does not exist, okay. So probably you can try to work it out a little bit and then we will continue. These problems are a little bit easy, so you can try to work it out. When there is a hard problem comes, then I will do much of the work. Okay, so let's try to prove it here. So you want to find the limit t tends to 0, 1 plus cos 2t by t, right? Now you replace by cos 2t with this formula. So this is nothing but limit the t goes to 0. You have 1 minus 2 sine square t by t. Right? So this is what you have now. So this okay, it might not exist here. You are right. 1 plus what 1 plus? So that is 1 plus that 2 sine square t here. Yeah, okay, okay. Thank you. Yeah, there is another one here, right? So I missed that. Yeah, okay, thank you, thank you, thank you. I missed it, yeah. So this is 2 plus 2 sine square t by t. So now we have to apply limit t tends to 0. Yeah, I think it does not exist only. What minus? Oh, okay. Okay, sorry again. Okay. Just give me 1 minute. I just want to see it's a cos square t square t by t, right? So that does not help me. Okay, just give me 1 minute. I just want to check something. I think it does not exist, but I just want to make sure that I'm right. I'm not telling something. If the answer is would have contained, the limit would be 0. Yeah, yeah, but the t below is actually there. That is the problem. Okay, yeah. Fine. The question says that there is a minus here. Yeah, exactly. Whatever you said is the thing. Yeah. Okay. I copied yeah. So I have some list of questions. Then when I copied it, I changed the sign here. But anyway, it doesn't matter. In the question it has the minus here. So that was I was wondering. Okay, why it happened. See, sometimes you can just do it and it will be correct most of the times. And what happens is when you're giving a lecture, you always prepare it beforehand so that make sure you will not do it. So when I was preparing, I had the minus here and then I changed it later, I think. When I'm writing it, I'm changing it. So that's the problem. Okay, anyway, let's proceed with this problem now. And then we will do the other one also. Okay. So if we have whatever we have now, so what we have is this is a limit t tends to 0. This is 2 by t minus limit t tends to 0, 2 sine square t by t. Okay. So if you just look at this part is 0. This goes to 0. So why? Because this is okay. Let's leave whatever it is. Yes, limit t tends to 0, 2 sine t by t times limit t tends to 0 sine t. Okay. So if you look here, this is a 1. So this is not 1. This is basically 2. This part is 2. But this part is 0. Sine t as t goes to 0 is 0. So as a whole, this will be 0. But when you come here, so as t goes to 0, 2 by t kinds of it blows up. So this limit does not exist. Okay. So it does not exist. So yeah, whatever you have said is right. In the case, okay, but what are the question I have prepared is the other one. So I will just do that also. So in the other one, instead of the plus here, you will get a minus. So it's just a minus here. So it's minus cos 2t. And simply because the limit e cos 2t by t does not exist as t tends to 0. Uh, so why cos 2t by t does not exist? Well, I mean, one can say the same thing because one is a bounded, another kind of blows up. So, yeah, that is true. See, because if cos 2t is also, I mean, if the above function is also going to infinity, then you cannot make, see, if it's something like infinity by infinity, then you cannot say anything. For example, you have something, let's say x by x. So both terms goes to 0 as infinity. Then if you look at even limit x goes to infinity, and if you look, then this will not happen. I mean, this will be just one only. Or maybe I don't want to write limit infinity, so let me write x goes to 0. If I write something like 1 by x by 1 by x, then this limit is basically just 1. Okay. But on the other hand, if one of that is bounded and the other one goes to infinity, then this limit does not exist. Okay, so since in the case that cos 2t is bounded, then whatever you say in the comments is also true. But let's do this problem now. So I'll just, yeah, I'm not very good at trigonometry though. So it's 1, I'll just copy the equation, sorry about that. So 1 minus 2 sine square t by t. Now the 1 get cancelled and this changes to plus. So you will get nothing but a 2 sine square t by t. Now you are applying limit as t tends to.
So we will get 2 cos square t by t.
Uh-huh.
2 cos square t by t, sir. Because the
Where?
cos 2t is okay, so you have changed the function.
Yeah. Is that fine?
You are writing the same function or you have changed the sign between 1 and
Yeah, it's
cos
the
2?
same function. I just changed this sign.
Okay.
This positive to negative there. Because when I change the sign, this one will get cancelled with that one.
Yes, sir. Yes.
But in this case, it will not get cancelled. That's the problem. Yeah. So, I mean, I was creating a problem such that it gets some value, but then when I write it down, I changed it. Yeah.
Sir, we can get 2 cos square t by t in that case.
Which case?
Because, sir, in the first case,
Huh.
2 cos square t by t.
2 cos 2 cos t by t.
2 cos square t by t. Because sir, cos
Okay.
2t is 2 cos square t minus 1.
Okay. Okay. You are telling such a limit exists, right?
No, sir,
Uh,
I am not, sir, convinced with your explanation why
which,
this
which
limit
which
does not
part?
exist.
Which part?
The
Limit does not exist here.
yes, sir.
Yeah. So
The
what I
limit
was
t
doing is
tends to
that
0 2 by t. Can we not say that it is plus infinity? It tends to infinity.
yeah, it tends to infinity. Yeah. But when it tends to infinity, we can just say limit does not exist. Or is the limit as infinity is defined? Can the
So
limit be
limit
infinity?
does
That
not
depends.
exist. So limit does not exist at all, or it just tends to infinity. Because if the function is tending to something, then we can say limit exists. So
No,
if
but
if
see,
it
if I'm right, what we define is the following, right? So we define using epsilon delta. We say let L belongs to a real number. Uh, suppose so whenever we say that limit of this x tends to infinity equal to f of x is equal to L, then there is a definition, right? For all epsilon, there is a delta, etc. You remember, right? So whenever we are writing the definition of the limit, it is understood the limit has to be a real number. Okay, because you are writing something like for all epsilon greater than 0, there exists a delta greater than 0, such that f of x minus L is less than epsilon. Whenever so x minus a is less than delta, you are writing, right? So whenever you write something like that, see, this L has to be a real number, and it's always understood the limit is a real number. So when the limit kind of blows up, we tell it does not exist, but of course there's a difference between the two-sided limit comes and then it is different, and then the another case where it just diverges, both diverges. So it's a possibility. Sometimes one side diverges, another side comes somewhere. So possibilities are many, but usually we say it does not exist only. At least that's the terminology I want to use. Maybe one can say it goes to infinity also. That is fine. If you can define, so to define that it goes to infinity, the limit is infinity. You have to define what is the limit at infinity. So usually when we begin the definition of limit, we kind of understood that this is infinity. So this L is a real number. Okay. So whenever I write something
Okay.
like that. But one can, of course, whatever you said, one can, of course, define what is the limit when the limit can be infinity. One can define, but you have to change the definition here a little bit. Once you change it, basically, instead of doing like that, you will just say f of x is greater than or equal to n for all natural number or something. You will write something like that. Okay, but you have to change the definition a little bit to make the limit at infinity to make sense. The limit is
Okay,
plus
sir.
infinity depends upon t tends to 0 in the left or right. So either way, limit does not exist. Okay, okay. Yeah, so yeah, okay, that is a one thing. Yeah, okay, that is also true because as it goes, you have either plus infinity or minus infinity for this one. But of course, one can talk about limited to infinity, and even say when a function tends to infinity, etc. But they want us to change the definition, but whatever the definition we have does not capture it yet. Maybe we'll do it later, or yeah, one has to see as the course proceeds. But it is possible to define such a terms. It's not impossible. Okay, so in this case, okay, I will just continue from here. So this is the problem we have, and instead of cos 2t, I'm just substituting, and these things get cancelled, and the sign will change by minus minus get plus. So this is what we have right now. So this you just look at 2 sine t by t, and then times you take sine t. Now we are applying limit t tends to 0. So this limit can be split into two limits. So you have something like if you have a limit of f and g, f times g, then the limit is nothing but limit f times limit g. So it's like a product rule is there. So this will be limit t tends to 0 to sine t by t, limit t tends to 0 sine t. Okay, and this limit is 1 and this limit is 0. So overall you get 1 times 0, which is 0 again. Okay. Okay, this is good. So, so how many of you understood that epsilon delta definition that was given in the lecture? So the limit has a definition, right? You understand. Okay, good. So if you have any doubts with that, trying to understand it, you can ask me, so I can help you with that. Okay. Either you can mail me. I can probably give you my email ID. I'll probably write it in the beginning. So you can mail me, or you can ask towards the end of the lecture also, because at least I remember whenever I did it, it took me some time to understand. Okay, yeah, you understand, but the intuition is lacking. So yeah, if you want intuition or you want to some help, then I can help you with that. But you can turn on the mic and we can discuss towards the end of the thing. We can discuss. Okay, so this is my email ID. You can send it. It's basically ISER. Okay. So I remember that I have studied this limit when I was in my 11th grade or something. Because 11th standard we have the limit thing, and my brother was doing BSc mathematics at the time. So he was telling me, see, the book only tells you this, but then there is a definition, etc. So whenever I try to understand, I remember that 3 months I was not able to get the intuition, but finally at some point you will get it. So At least at that time, whenever I studied it first, I find it little hard that, see, it's not little hard for us also, not only for us. See, whenever the Newton defined it, he defined it in terms of, there's something called delta y, delta x, and they called it infinitesimal, etc. It's infinitesimally small quantities, etc. But one has to make sense of it. It took almost 100 years for the definition of limit to come. So derivative was there even before the definition of limit comes. After the definition of limit comes, the derivative was defined in terms of the limit. But now if you study the course, the limit comes first and the derivative comes after that. But historically, derivative comes almost a century before the definition of limit was there. So yeah, the intuition was lacking. Yeah. So it's not very intuitive anyway. It was a little bit hard anyway. Okay, I think, okay, these are the questions I have. Maybe I will just add one or two because we have to take some time, right? So let me try to get a good question here. Okay, so let's do the fifth question here. If AB equal to AC for some ABC belongs to integers, then B equal to C. So it is true or false? Okay, why it is false? Yeah, so false is the right answer, but why it is false? Yeah. Okay, so we have two answers here. I will just I will try to explain both. Only thing is, one of the answer requires a little bit of group theory, or at least group theory or field theory, something like that, which is not needed for the course. But we will do both. I mean, if you don't understand, you can just ignore it. It's fine. Okay. So as the Advait said, if A is 0, then you can take anything. Okay. So I think, yeah, at least two people have said some. If A is 0, then you can take. So that is true. If A equal to 0, then you take AB, that is 0. So probably you take the example like that: A equal to 0, B equal to 2, and C equal to 3. Then you have this AB equal to AC equal to 0. Okay. Yeah, that was the trivial case. Yeah, that is true. If you take anything else, okay, then what about if none of them are 0? If none of the ABC are 0, or let's say A is not equal to 0, then what happens? Then what happens? Yeah, for Z only. Yeah, then it is true. Exactly. Yeah, I actually see Sandeep were telling that you need inverse. Yeah, that is true. Z does not has an inverse, but Z is contained in Q, right? Let's say Z is contained in Q or R. The inverse is there, right? So you have AB equal to AC, but then you take the inverse. You cannot have the inverse here, but then you go to the bigger one where you have the inverse. So you multiply both sides by 1 by A. And whatever happens here, it should be true here also. So you can cancel out here. Okay, so then you will get B equal to C. Okay. Or if you want to do a little bit more, you can take AB minus AC, and then you can take A, b minus c. This is 0. So yeah, you might know that z is an integral domain, right? So you can use something with it. But anyway, that is not needed. Yeah, so you can take the inverse in the bigger one, and then you can get this. Okay, let's do maybe one question maybe. Probably we'll do one calculus question and we'll stop. There's not many good calculus questions. I will do this one. This one was interesting. Okay. If y1 and y2 are two functions, not such that y1 of x so what is the domain of y1 by y2? It's R, okay. I will I mean, so it's basically the function, if you look, it is basically 2 by x square plus 1, right? So as long as this term is not negative, this as long as the x square minus 1 is not equal to 0, this makes sense, right? See, I can write, I can divide two real number as long as the denominator is not equal to 0. So it's all okay as long as x square plus 1 is non-negative, right? So how do you say x square plus, sorry, as long as it is not 0. So how do you prove that x square plus 1 is not equal to 0 for all x belongs to R? If you prove that, then the domain is R, right? Otherwise, you have to avoid the case where the x square is equal to minus 1. Okay. So how do you prove this is true? Yes, exactly. It's greater than or equal to 1 for all x. So if you look at x square is positive, right? It's greater than or equal to 0. So if you go for x square plus 1, so x square plus 1 is always greater than or equal to 1. So it is never 0, right? So this term is never 0. So you can divide by that and you can do. So in another thing, what you do is you can see is this equation does not have a solution in R. Okay. But anyway, that is some algebraic way, but we don't need that. Okay, so these are the problems. We can stop here. And if somebody has any doubts or something, you can ask me. So the class was over and you can leave now. Anybody who has the doubts or something, you can ask me later. Yeah, you can ask real analysis doubt, but then probably let's the other people who has the doubt in the course can ask. After that, probably you can ask. So I will stop the recording. After that, you can ask. Okay. If there is no doubt, I will turn off the recording. So we will see in the next class. Bye.